Yet recently a tremor ran through this grand vision. A routine ground test, meant to inch humanity closer to the stars, instead delivered a jarring setback. The footage, stark and unyielding, showed an anomaly, a sudden violent release of energy that left behind not the triumphant roar of a successful test, but the unsettling silence of shattered hopes. Was this merely a minor stumble on a long, arduous journey, a transient blip in a relentless march towards Mars? Or could this incident, seemingly isolated, be a harbinger of deeper, more insidious problems, the kind that could unravel years of relentless innovation and, with it, the very fabric of our interplanetary ambitions? The stakes have never been higher. What exactly transpired at the dusty expanse of Boca Chica, Texas, a place synonymous with the relentless pursuit of rocket engineering? The stage was set for a static fire test of a Starship prototype, one of the many iterative versions designated with an SN serial number, each a stepping stone in the rapid development cycle. These tests are not mere formalities, they are brutal crucibles where raw power meets cutting-edge engineering, pushing systems to their absolute limits, simulating the immense forces a spacecraft will endure during launch. The very air around the test stand thrummed with a nervous energy, pregnant with anticipation, as engineers meticulously prepared for the fiery ballet of engine ignition. The procedure itself is a symphony of precision: propellant loading, final system checks, then the countdown to the moment of truth when the mighty Raptor engines are briefly ignited while the vehicle remains tethered to the ground. This particular test was designed to validate engine performance, structural integrity under thrust, and the complex interplay of cryogenic propellants. Every second, every pressure reading, every vibration, was meticulously monitored by an army of sensors, feeding critical data back to the control room. The hope was for a clean burn, a sustained roar, and a successful shutdown, paving the way for further, more ambitious flight tests. But then the expected roar morphed into something else entirely. Instead of a controlled ignition and a steady column of flame, a violent, instantaneous event unfolded. Depending on the specific test, it could have been a sudden, uncontrolled pressure release, a structural rupture, or in some cases what SpaceX euphemistically terms a rapid, unscheduled disassembly, an explosion. The failure points were starkly visible in the aftermath: twisted metal, debris scattered across the pad, and the telltale signs of immense energy dissipation. The severity of such an event cannot be overstated. It's not just a blown fuse, but a fundamental breach of containment or structural integrity. The immediate aftermath was a scene of controlled chaos. Engineers, while undoubtedly disappointed, immediately pivoted into their core function: problem-solving. Every piece of telemetry, every video frame, every scrap of recovered hardware becomes a crucial clue in a high-stakes forensic investigation. The goal is not to assign blame, but to understand precisely what went wrong, to pinpoint the root cause among a myriad of complex interacting systems. This rigorous postmortem is paramount, because in the unforgiving realm of rocket science, even the smallest oversight can lead to catastrophic consequences, and the next test depends entirely on absolute clarity. Now we delve deeper into the labyrinth of possibilities, seeking to unravel the specific issues that might have led to this unsettling setback. When a ground test fails, the potential causes are often multifaceted, intertwined in a complex web of engineering challenges. It's rarely a single, isolated factor, but rather a confluence of stresses, design tolerances, and operational parameters pushing the limits of current technology. Understanding these potential causes is critical not just for SpaceX, but for the entire aerospace industry, as the lessons learned from such incidents propel future advancements and safety protocols. One of the most immediate suspects in any rocket test anomaly is the engine itself. In Starship's case, this points directly to the revolutionary Raptor engine, a beast of an engine that burns liquid methane and liquid oxygen, employing a full-flow staged combustion cycle, a design so complex and powerful that only a handful of nations have ever even attempted it, let alone mastered it. The Raptor is designed to deliver unprecedented thrust-to-weight ratios and efficiency, critical for Starship's full reusability and audacious payload capacity. But with groundbreaking technology comes uncharted territory and inherent risks. Potential issues with the Raptor engine could range from the seemingly mundane to the utterly catastrophic. Was it a problem with propellant mixture ratios, leading to unstable combustion within the chamber? Perhaps a turbopump, spinning at tens of thousands of revolutions per minute and operating under extreme pressures and cryogenic temperatures, experienced cavitation or a bearing failure, leading to a sudden loss of thrust or worse, an explosion of its own. Combustion instability, where pressure oscillations within the engine grow uncontrollably, is another perennial challenge in rocket engine design, capable of tearing an engine apart in milliseconds. Then there's the insidious threat of material fatigue, where repeated thermal cycling or prolonged exposure to cryogenic propellants can weaken critical components over time, leading to microfractures that propagate under stress. Even microscopic imperfections in a weld or a casting can become critical failure points when subjected to the brutal environment inside a rocket engine. The very design of the Raptor, with its intricate internal plumbing and high-pressure components, means that any deviation from nominal operation can rapidly escalate into a severe anomaly. The precision required is almost unfathomable. Beyond the engines, the very body of Starship itself, its structural integrity, comes under intense scrutiny. Unlike traditional rockets made of exotic carbon composites or aluminum alloys, Starship famously employs stainless steel. This choice, initially met with skepticism, offers significant advantages: cost-effectiveness, ease of manufacturing, and excellent strength at cryogenic temperatures, crucial for holding supercooled methane and oxygen. However, stainless steel also introduces its own set of engineering challenges, particularly concerning its weight and the complexities of welding thick sections while maintaining structural uniformity. During a static fire test, the Starship structure is subjected to immense forces. The downward thrust of the engines attempts to tear the vehicle from its moorings, while the colossal weight of the cryogenic propellants exerts inward and outward pressures on the tank walls. Points of stress concentration, such as where the engines are mounted to the thrust puck, or where the various tank sections are welded together, become critical junctures. A slight flaw in a weld seam, an overlooked stress point in the design, or even an unexpected material property under extreme load could manifest as a structural weakness, leading to a rupture. Imagine the sheer force. Millions of pounds of thrust pushing against a structure filled with supercooled liquids. If there's a hairline crack, a microvoid, or an area where the material behaves unexpectedly, this is where it will give way. It's a delicate balance of engineering, optimizing for weight reduction while ensuring robust strength. The analysis here would involve meticulous examination of the wreckage, looking for the telltale signs of a primary structural failure, whether it originated in the propellant tanks, the interstage, or the thrust section itself, which supports the entire engine cluster. Finally, we must consider the intricate dance of integration challenges, the unseen complexities of how all of Starship's disparate systems communicate and operate in harmony. Starship is not just an engine and a tank. It's a marvel of integrated engineering comprising engines, propellant lines, pressurization systems, avionics, flight computers, thousands of sensors, and complex control mechanisms. A failure in one seemingly minor component or software system can trigger a catastrophic chain reaction throughout the entire vehicle, akin to a single misplaced domino toppling an entire elaborate structure. Consider, for instance, a valve responsible for regulating propellant flow. If it malfunctions even for a split second, it could lead to an incorrect mixture, a pressure surge, or a sudden starvation of an engine, inducing an anomaly. Similarly, a sensor giving an erroneous reading could cause the flight computer to issue an incorrect command, pushing a system beyond its safe operating limits. Software glitches, timing issues, or unexpected interactions between different subsystems can also be silent saboteurs, difficult to diagnose until a failure occurs. The synchronization of multiple Raptor engines during ignition and operation is another Herculean task. Each engine must ignite and ramp up thrust in perfect concert. Any significant asymmetry or delay could induce uncontrolled stresses or lead to a vehicle instability. This requires incredibly precise control systems and robust feedback loops. The iterative nature of Starship development means that new systems are constantly being integrated and tested, increasing the potential for unforeseen interactions or ghosts in the machine that only reveal themselves under the most extreme conditions. The path forward demands an unwavering commitment to unraveling every layer of this intricate puzzle, for the dream of Mars, the dream of humanity's expansion, hinges on it. The path forward, as we've seen, demands an unwavering commitment to unraveling every layer of this intricate puzzle, for the dream of Mars, the dream of humanity's expansion, hinges on it. But what are the tangible consequences of such a high-profile failure? Beyond the immediate technical setbacks, the ripple effects can be far-reaching, impacting not just SpaceX's internal operations, but the very trajectory of humanity's off-world ambitions. This single violent event sends tremors across the entire landscape of space exploration, forcing a re-evaluation of timelines, budgets, and even the fundamental approaches to conquering the cosmos. The stakes are immense, and the shadows cast by this failure stretch long across the red plains of Mars. Perhaps the most immediate and agonizing impact of any significant setback in spaceflight is the inevitable delay to existing timelines. SpaceX operates on an incredibly aggressive schedule, driven by Elon Musk's fervent desire to make humanity a multi-planetary species within our lifetimes. Every Starship prototype, every static fire, every hop test, is meticulously planned as a stepping stone towards crewed missions to Mars, initially envisioned for the mid-2020s. A failure, even on a ground test, disrupts this meticulously choreographed dance, forcing engineers back to the drawing board, demanding redesigns, remanufacturing, and retesting. Each of these steps consumes precious time, pushing back launch windows that are already constrained by the fickle orbits of celestial bodies. Consider the orbital mechanics involved in Mars missions. There are only optimal launch windows every 26 months when Earth and Mars are aligned favorably for a shorter, more fuel-efficient journey. Missing one of these windows can mean a 2-year delay before the next opportunity arises. A series of failures or even a single complex issue requiring extensive re-engineering could easily cause SpaceX to miss multiple such windows, pushing their Mars colonization timeline not by months, but by years, perhaps even a decade. This isn't just a minor inconvenience. It's a profound shift in the very pace of humanity's expansion, a deferral of a dream that many believe is critical for our long-term survival. The ticking clock of planetary alignment adds an unseen layer of pressure, turning every setback into a race against cosmic time. Beyond the clock, there's the formidable barrier of cost. Developing a vehicle as complex and colossal as Starship is an astronomically expensive undertaking, even for a company as well-resourced as SpaceX. Billions of dollars have already been poured into its research, development, and testing. Each prototype, each engine, each test stand, represents a significant investment. A failure means not only the loss of the specific hardware involved but also the expenditure of immense resources in the forensic investigation, the redesign process, and the subsequent remanufacturing and retesting of components. This leads to escalating financial burdens, potentially straining budgets and diverting funds from other critical projects within the company. Moreover, the financial implications extend beyond the immediate costs of replacement hardware. Delays can impact investor confidence, affecting future funding rounds and the overall valuation of the company. Government contracts, which often have strict performance and timeline clauses, could also be jeopardized or renegotiated, further impacting revenue streams. The cost of a failed test isn't just the price of a rocket, it's the cost of lost time, eroded confidence, and the opportunity cost of resources that could have been allocated elsewhere. It's a sobering reminder that even the most ambitious visions must contend with the stark realities of financial viability. The dream of Mars, while boundless in its aspiration, is still tethered to the unforgiving constraints of the terrestrial economy. Yet, amidst the delays and the financial strain, there lies an undeniable truth. Every failure, however painful, is a brutal teacher. The very essence of engineering progress is born from understanding what went wrong and iteratively improving upon it. This ground test failure, despite its immediate negative impact, provides an invaluable dataset, a harsh but crucial lesson in the unforgiving physics of rocket science. It highlights vulnerabilities that might have remained hidden during simulations or less strenuous tests, forcing engineers to confront their assumptions and refine their designs. The knowledge gained from a single catastrophic event can be more profound than years of nominal operations, shaping the technological advancements of the future. This means a deeper dive into materials science, perhaps exploring new alloys or manufacturing techniques to mitigate structural weaknesses. It could lead to refinements in engine design, making the Raptor even more robust and tolerant to unexpected operational parameters. It will undoubtedly result in more sophisticated sensor arrays and diagnostic tools, allowing engineers to catch subtle anomalies before they escalate into full-blown failures. The very process of learning from failure pushes the boundaries of technological innovation, ensuring that the next iteration of Starship is not just repaired, but fundamentally improved, made more resilient, more reliable, and ultimately safer. The path to the stars is paved not just with ambition, but with the hard-won wisdom gleaned from every stumble. So, what does this mean for the road ahead? How does SpaceX, a company known for its relentless optimism and rapid iteration, address such a significant setback? The first and most crucial step is a comprehensive and unflinching investigation into the identified problems. This isn't a superficial glance. It's a deep, systematic forensic analysis, utilizing every scrap of data, from telemetry logs to recovered debris, to reconstruct the precise sequence of events that led to the anomaly. Specialized teams of engineers, metallurgists, software developers, and propulsion experts will meticulously pore over every detail, seeking the root cause, no matter how small or seemingly insignificant. Once the root cause is identified, the arduous process of redesign begins. This could involve strengthening specific structural sections, modifying engine components, or refining software algorithms that control the vehicle's systems. SpaceX's unique approach to rapid prototyping allows for quick implementation of these changes, building new iterations of Starship with the lessons learned immediately incorporated. This agile development cycle, while sometimes leading to dramatic failures, also allows for an unprecedented pace of innovation and problem-solving, a stark contrast to the often glacial progress of traditional aerospace programs. The next steps for Starship will undoubtedly involve a renewed series of ground tests, pushing the redesigned components and integrated systems to their limits. These tests will be even more critical, serving as validation points for the implemented fixes and building confidence in the vehicle's readiness for more ambitious flight attempts. The public will be watching, holding its breath with every static fire, every pressure test. Success in these iterative steps is paramount to regaining momentum and reassuring both investors and the public that the dream of Mars is still within reach. The path will be long, arduous, and punctuated by further challenges, but the commitment remains unwavering. But what if, despite their best efforts, the challenges prove too formidable, too persistent? What if Starship, in its current iteration, encounters fundamental design limitations that make its envisioned role untenable? While highly unlikely given SpaceX's track record of overcoming seemingly insurmountable obstacles, contingency plans are always a part of responsible long-term vision. This doesn't necessarily mean abandoning Mars, but perhaps exploring alternative pathways or technologies. It could involve developing a different heavy-lift launch system, or partnering with other aerospace companies to achieve the necessary capabilities. However, for a company like SpaceX, contingency plans are rarely about giving up on their core vision. Instead, they typically involve re-evaluating the approach, perhaps extending timelines further, or breaking down the problem into smaller, more manageable phases. It could mean focusing initially on moon missions as a proving ground, accumulating invaluable operational experience before attempting the more distant and challenging journey to Mars. The resilience to adapt, to pivot, and to find new solutions in the face of adversity is perhaps the most crucial characteristic of any successful endeavor into the unknown. The human spirit, when confronted with the vastness of space, rarely accepts defeat. Ultimately, the significance of the Starship program transcends the success or failure of any single test, or even the immediate timelines for Mars. It represents a fundamental paradigm shift in how humanity approaches space exploration. For decades, spaceflight was the exclusive domain of governments, characterized by bespoke, expensive, and largely disposable rockets. Starship, with its focus on full reusability and mass production, promises to democratize access to space, making missions to the Moon and Mars not just possible, but economically viable on an unprecedented scale. This is about making space accessible, routine, and ultimately, a place where millions can live and work. This ambitious program also has profound implications for the new space race. While not a direct competition between nations in the Cold War sense, there is an undeniable race to establish a permanent human presence beyond Earth. Starship's success would give SpaceX, and by extension the United States, a significant lead in this burgeoning domain, potentially shaping the geopolitical landscape of the cosmos. It's about more than just flags on distant worlds. It's about controlling critical resources, establishing vital infrastructure, and pioneering new frontiers that will define the next chapter of human civilization. The future of space exploration, once a distant fantasy, is now a palpable race, and Starship is at its forefront. And perhaps most importantly, the relentless pursuit of Starship, despite its setbacks, inspires. It ignites the imagination of a new generation, reminding us that the greatest challenges are also the greatest opportunities for innovation and discovery. Every launch, every test, every image of a towering Starship prototype whispers a promise that humanity is not destined to remain confined to a single planet. It encourages young minds to pursue careers in science, engineering, and technology, fostering the very intellectual capital required to tackle the grand challenges of our time. The journey to Mars is not just about rockets and engineering. It's about pushing the boundaries of what is possible, instilling a sense of wonder and reaffirming humanity's innate drive to explore the unknown. The echoes of a static fire failure may linger, but the call of the cosmos, amplified by Starship's audacious vision, remains an irresistible siren song, drawing us ever closer to the limitless possibilities of the universe. The future, though momentarily delayed, still beckons with the promise of worlds yet to be touched.